Imagine hiring the absolute smartest PhD on the planet. I mean,
Uh,
someone who can write flawless code, draft brilliant marketing copy, and, solve complex probabilistic math in seconds.
Right, that sounds like a dream hire.
Yeah, totally.
yeah.
But there is a massive catch. Every single morning, this genius employee wakes up with total amnesia.
Oh, wow.
Right. You have to sit them down and re-explain what your company actually does, who the CEO is, where the database passwords are stored, and even what project they were working on just yesterday.
That sounds exhausting.
It is. That friction completely cancels out their genius. You'd spend all your time just bringing them up to speed. And for anyone trying to build real, durable systems with AI right now, that is exactly the problem you're facing.
Yeah, that friction is the defining bottleneck in enterprise AI today. We spend so much time obsessing over raw intelligence. Like, every time a new model drops, we all look at the benchmark scores.
Right. The newest release is always the smartest.
Exactly. But in a business environment, raw intelligence doesn't naturally compound. A brand new top-tier model doesn't magically know your proprietary codebase out of the box, and it certainly doesn't know your specific user preferences.
Because it resets every time you open a new chat window.
Precisely. So today's deep dive is about a masterclass on how we actually solve that. We're looking at a presentation from the AI Native DEF CON in June 2026 by Lamas Mukta from Anthropic.
Yes, the Anthropic presentation, it was so good.
It really was. We're looking at a brand new engineering frontier that takes AI agents from being brilliant amnesiacs and turns them into continuous learners.
Okay, let's unpack this, because if you're listening to this, you've probably felt that exact pain point. You want the compounding value of an AI that gets to know your workflow.
Without drowning in the frustrating cycle of, constantly tweaking your prompts.
Yes, reminding the AI how you like things done every single time. What Mukta is talking about here is called context engineering.
Right. Context engineering is essentially the lever that takes baseline AI intelligence and multiplies it for your specific use case.
And what's wild is how fast this is moving.
Oh, totally. What's fascinating here is how rapidly this specific field has evolved. Mukta noted that this entire timeline, going from basic text files to AI architectures that essentially sleep and dream, has exploded into a highly sophisticated discipline in just the past year.
Just 1 year. That's insane.
Yeah, and Anthropic's applied AI team, they operate on this guiding philosophy of do the simple thing that works.
Which makes sense. Keep it simple.
Exactly. So to cure the amnesiac employee, their very first instinct was to just, hand the AI a manual when it walked in the door.
Right. Which makes total sense. Like, if I have a new hire, I give them an onboarding document.
Yeah.
And that's where Anthropic started, right?
Yeah, they started with something really basic.
Just a standard text file injected into the AI's memory at the start of a session.
They called them Claude MD files, just a standard markdown document, a highly readable, plain text file that you inject right at the beginning of an agent's prompt.
Just dropping it right in there.
Yep. You might put in a few paragraphs about how to navigate the local code base or maybe your personal formatting rules for writing emails. And Mukta mentioned it was unreasonably effective early on.
Unreasonably effective. I love that phrase.
Right. Just a plain, human-readable text document that steered the agent perfectly.
But handing someone a manual every morning only works if the manual is, brief.
Exactly.
If that instruction file turns into a 1,000-page encyclopedia covering every possible edge case in a global enterprise, you're going to break the system.
Yeah, you run into what they call context bloat.
Context bloat.
Context bloat is the enemy of performance. Injecting massive amounts of memory into the beginning of a session gets incredibly expensive in terms of token usage.
Because it has to read the whole thing every single time.
Right, and it slows the system's response time to a crawl. But worst of all, mechanically, the AI's attention mechanism starts to degrade. It's the classic needle in a haystack problem.
Oh, where it just loses track of the instruction.
Exactly. If you buried a crucial instruction about database security on page 400 of a manual, the AI is highly likely to lose track of it while it's trying to answer a user's immediate question.
The raw volume of text just dilutes its focus.
That's exactly.
So handing the AI the entire encyclopedia up front fails. They needed a way for the AI to only read the specific chapters it actually needed for the task at hand.
Right, which brings us to progressive disclosure.
Progressive disclosure. And they initially tried to solve this through something called skills. And Lamas Mukta used an analogy in her talk that just perfectly crystallized this for me.
Oh, the bookshelf analogy.
Yes. She compared these skills to a bookshelf.
It's a great way to visualize how an AI manages its active working memory.
Imagine the agent is standing in front of a massive bookshelf full of reference materials. Instead of reading every single book before starting its job, the agent just scans the front matter.
Right, the titles on the spine.
Exactly. It reads the titles on the spines or maybe a one-sentence summary of what's inside. It only physically pulls a book off the shelf, opens it, and loads that massive amount of text into its active context window if the current task absolutely requires it.
And the example she used was a French dictionary.
Right, the French dictionary.
You don't need to hold the entire French language in your active, conscious working memory at all times.
No, that'd be a waste of brain space.
But if a user suddenly walks up and prompts you in French, you can glance at your bookshelf, spot the French dictionary, pull it down, and load that specific context into your brain for that single conversation.
Which is brilliant.
It is. It's a clever way to allow for incredibly deep, domain-specific knowledge without overloading the model's context window.
But wait, I had to push back on this a little bit.
Go for it.
If the agent is just scanning titles on a bookshelf, doesn't that inherently bottleneck the whole system?
How do you mean?
Well, it relies entirely on a human engineer perfectly labeling those titles in the first place. Like if I name the French dictionary something weird, or if I don't write the front matter summary perfectly, the agent never pulls it down.
That's a very fair point.
That doesn't sound autonomous at all. It sounds like a highly opinionated manual curation nightmare for the engineers.
You've hit on the exact limitation that forced Anthropic to evolve again.
Ah, okay.
Relying on humans to manually curate and meticulously trigger those specific skills just doesn't scale. The resolution to the state-of-the-art for memory systems today is to stop building hyper-specific, opinionated tools.
So what do they do instead?
They treat memory exactly like a traditional computer file system.
So instead of a curated bookshelf, you just give the AI a massive hard drive.
Basically, yes. You fill a directory with markdown files, and you give the agent standard, old-school software utility tools like Bash and grep.
Okay, grep.
Yeah, and for anyone unfamiliar, grep is a command line tool used by developers to search massive plain text data sets for lines that match specific keywords or expressions.
It's like the ultimate search function.
Exactly. And Anthropic realized you can just gill these terminal tools directly to the AI. You let the agent autonomously type out command line searches, read the output, and index the file system entirely on its own to find the memory it needs.
It's wild to picture a neural network typing out Unix terminal commands just like a human sysadmin trying to find a lost file.
It really is.
It's literally a search bar for its own brain. But here's where it gets really interesting. Because having an autonomous file system works beautifully when it's just one agent helping one person on a laptop.
Right, in a controlled environment.
But when you scale this up to an enterprise level, the entire theory completely shatters.
Oh, absolutely. This raises an important question. What happens when theoretical autonomy meets the chaotic reality of a live production environment? Total chaos. You are no longer dealing with a single agent on a local machine. You are dealing with fleets of agents, sometimes thousands of them, working concurrently in complex domains.
Imagine a shared Google Doc. If it's just you and 3 coworkers drafting a memo, it's fine.
Right, you can manage that.
But imagine 1,000 autonomous AI agents, all trying to type, delete, and edit that exact same document at the exact same millisecond.
It would crash instantly.
They're all trying to update their shared memory bank simultaneously. Plus, one of those agents might have just been maliciously tricked by a prompt injection from a user, and it's currently trying to delete the entire company codebase.
Or it's trying to write a terrible line of code that all the other agents are going to read and accept as a fact.
Yes, it's a total production nightmare.
But concurrency errors alone would crash the system. Anthropic realized that to make this autonomous memory work in production, they had to implement incredibly rigid guardrails.
Which Mukta went into in the presentation.
She did. She laid out a few critical solutions for this, starting with how to handle that Google Doc problem. To prevent 1,000 agents from overwriting each other, they use a hashing system.
Let's break down how that actually works under the hood, because hashing sounds super technical, but the mechanism is actually pretty elegant.
It is elegant. Think of a hash as a unique digital fingerprint for a document at a specific moment in time.
Okay, fingerprint.
When an agent decides it needs to update a shared memory file, it first takes a snapshot of the document's current fingerprint. Then, the agent goes off and does its thinking.
Which takes a bit of time.
Right. It drafts its edit, which might take a few seconds or a minute. Right before the agent hits save to commit that edit, the system forces it to check the document's fingerprint one more time.
Oh, so it's basically a temporal lock. If the second fingerprint doesn't perfectly match the first one, it means another agent snuck in and changed the document while the first agent was thinking.
Exactly. The first agent is immediately blocked from writing. It's forced to drop its edit, repull the newly updated memory from the system, and start its thinking process all over again.
That's brilliant.
It physically cannot overwrite someone else's work or create branching, conflicting realities in the memory bank.
Okay, so they can't accidentally overwrite each other. But what about the security side? What stops one rogue agent who maybe learned a bad habit or got tricked by a user from permanently ruining the master company instructions?
That requires the second guardrail, strict permissioning boundaries.
Provisioning.
You have to physically separate the global organization-wide context from the individual agent's working memory. The organization-wide knowledge, the core principles of your codebase, your brand voice, your immutable security rules must be strictly read-only for the active agents.
So they can look at the master file, but they cannot touch it.
Exactly, they cannot touch it. However, all the way down at the individual task level, each agent is given a read and write scratchpad.
A scratch pad.
It's their own private sandbox where they can take notes, fail, and update their immediate working memory without polluting the global pool.
Okay, so the scratch pad keeps them from ruining the master file. But if they're learning all these great lessons in their own little sandbox, how does the rest of the company actually benefit from it?
Right, how does it spread?
Do those memories just die on that one machine when the session ends?
Well, they would unless you build in portability. If an organization spends months carefully curating these memory systems, that intelligence needs to be accessible across multiple product surfaces via clean APIs.
Okay, so they can talk to each other.
Right. During the Q&A portion of the DevCon presentation, Mukta mentioned that all of this, the hashing for concurrency, the permissioning boundaries, the APIs for portability, is actually handled out of the box via Claude-managed agents now.
Oh, nice.
And the irony here, which she openly acknowledged, is that AI engineers aren't really inventing new computer science to solve this.
What do you mean?
They are essentially just reinventing foundational database and software engineering principles from the 1970s and 80s.
That is such a wild realization. For years, AI models were basically treated as these unpredictable black box slot machines.
All right, you just pull the lever.
You pull the prompt lever and hope for a good output. You could never plug them into a rigid, traditional database structure because they hallucinated too much.
But the models have crossed a threshold. Autonomous agents finally have enough signal, they are deterministic and reliable enough that we can merge them back into these proven, decades-old software engineering practices.
We can safely give them version control.
Exactly. We can give them version control, concurrency locks, and read-write permissions because they are finally mechanically stable enough to use them properly.
Okay, so we've solved the database problem. The amnesiac employee now has a perfectly organized, highly secure filing cabinet that they can search through autonomously, and they physically cannot set it on fire.
Safe from the fire, yes.
But even with perfect database rules, we hit another wall, because having the agent try to update its own memory while it's actively helping a user exposes a fatal philosophical flaw in the architecture.
Yes. Mukta refers to this as the trap of in-band memory.
In-band memory.
In-band memory means the agent is being asked to read, evaluate, and write to its long-term memory during a specific active session with a user.
They are trying to complete the complex coding task you just assigned them, while simultaneously trying to curate their knowledge base for tomorrow.
Which is incredibly taxing.
If you've ever used an AI and gotten frustrated because it completely forgot a formatting rule you gave it just 3 prompts ago, this is why.
Exactly.
Asking an agent to do that is like asking me to write a massive, highly technical research paper while simultaneously updating my resume, organizing my 5-year life goals, and filing my taxes.
It's an impossible split of focus.
You cannot be fully present and creative in the immediate task if you are constantly indexing your own brain for future utility.
Mathematically, Anthropic found this creates a massive optimization problem for the system.
Because of the tokens.
Exactly. The agent only has so much compute capacity, so many tokens it can generate per second. How much of that token budget should it dedicate to helping a future version of itself learn versus actually answering the user who is staring at a loading screen right now?
The user is just waiting.
Right. It introduces unacceptable latency and inflates the cost of the session. But beyond the split focus and the cost, there is a much deeper inherent visibility limitation with in-band memory.
Because the agent can only see what's right in front of its face in that specific chat window.
An agent working in-band is trapped in the context of its current session. It fundamentally cannot spot fleet-wide
Oh, I
patterns.
see.
Let's say you, the user, get annoyed because the agent keeps making the exact same indentation error in your Python code every single time you spin up a new session.
So frustrating.
Very, but the agent doesn't realize it's a chronic problem. To the active agent, every new session is a blank slate. It has no idea that its peer agents, working with entirely different users across the company, are running into the exact same failures. It can't zoom out.
So what does this all mean? How do you actually get an AI system to learn from its mistakes if it doesn't have the compute bandwidth to learn while it's actively working and structurally blind to the big picture?
It means you have to let the AI process things when it's not working.
Okay.
You have to take memory curation completely out of band. And Anthropic's paradigm for doing this is a deeply human concept. They call it dreaming.
Dreaming.
Dreaming. It is a curation process that runs asynchronously, in batch, entirely separate from active user sessions.
So like at night.
Usually at night, yeah, or during low traffic periods. Organizations dedicate compute resources and token spend solely to this background process. The tokens aren't being used to answer user prompts. They are purely dedicated to helping the fleet of agents learn.
I love this concept. Mukta used a school analogy to explain the mechanics of how dreaming actually works, right? The students and the head teacher.
Yes. Think of the active daytime agents as students. During the day, the students are just focused on taking the test.
Just getting through the work.
Exactly. They are just trying to get the immediate answers right for the user. They aren't trying to write the curriculum. But at night, a separate, highly capable orchestrator agent steps in to act as the head teacher.
The head teacher.
This head teacher agent reviews all the transcripts, all the submitted work, and all the scratch pads from every single student across the entire enterprise fleet, looking for global patterns.
And the example she gave of what the head teacher spots are brilliant.
They really are.
The orchestrator reviews the transcripts and notices, like, wow, literally every single student is failing the geography questions today. It's not because the daytime agents are suddenly bad at geography. It's because the head teacher realizes geography is entirely missing from the core organizational memory store.
Exactly.
Or, in a coding context, the head teacher notices on a fleet-wide level that every single agent is using way too many M dashes in their marketing copy, which violates the brand guidelines.
It catches those broad trends.
But I have to ask about the mechanics of this. How does the head teacher actually know why something went wrong? Because if it's just reading the chat logs between the user and the AI, sometimes a chat log doesn't explain the failure.
That's true.
It just shows the AI giving a wrong answer and the user saying, like, no, that's wrong.
That distinction is crucial. The orchestrator isn't just skimming the conversational back and forth text. During this dreaming phase, the head teacher deploys a fleet of subagents that heavily scrutinize the hidden metadata.
The metadata.
They are looking at the specific tool calls the agent made behind the scenes.
What's an example of a tool call failure?
Well, take a math exam. The head teacher notices every student is getting a trigonometry question wrong. The subagent digs into the metadata and realizes the agents are outputting their answers in radians instead of degrees. Right. And the subagent looks at the tool configuration and realizes the internal calculator tool the agents were given was defaulted to radians, and the agents didn't know they needed to switch it.
Wow.
The orchestrator is diagnosing underlying mechanical failures, not just conversational missteps.
Okay, so the head teacher successfully diagnoses the systemic problem. What happens next? Does this orchestrator agent just automatically rewrite the company's core memory bank?
No, definitely not.
Because giving an AI the power to autonomously rewrite the global master file while everyone is asleep sounds a little bit terrifying.
Anthropic doesn't automate that final step, precisely because of that risk. The orchestrator agent identifies the prevalent patterns and then proposes a highly optimized update to the memory store.
Proposes.
Right. It doesn't just send a generic alert saying, change the math tool. It builds a comprehensive case.
Like a real teacher making a curriculum proposal.
Exactly. It provides statistical data on exactly how prevalent the error was across the fleet that day, and it attaches specific transcript examples to prove its hypothesis. It presents this entire neat package to a human overseer.
So the human engineer just logs in, drinks their morning coffee, and reviews a curriculum update that was fully prepared by the AI based on the AI's own analysis of its systemic failures.
Yep.
And if the human clicks approve,
the global memory store is updated. And the tangible business result of this is massively lower costs and lower latency.
Because it fixes the root cause.
Exactly. Because the next day, when the student agents wake up and pull from the newly updated memory store, they don't have to stumble through 5 prompts of trial and error to get the math right. The calculator is
It's
fixed.
huge.
They can just one-shot the task. They get it right on the very first try, which saves a massive amount of compute power and creates a magical experience for the user.
It is incredible. The scale of this evolution is just staggering to me. We have gone from injecting simple static text files into an AI's prompt, hoping it remembers our name, to building robust file systems with database locks.
Yeah, full operating systems.
And now to literally designing enterprise AI architectures that sleep. They go offline, analyze their fleet-wide failures in the dark, propose rewrites to their own cognitive rulebooks, and wake up fundamentally smarter the next day without any human having to manually dig through code to figure out what went wrong.
If we connect this to the bigger picture, this dreaming architecture is what separates a generic, out-of-the-box AI model from a truly customized compounding intelligence.
It's a completely different level.
As Lamas Mukta emphasized, this is a brand new frontier in software engineering. The transition from brilliant amnesiacs to continuous learners is the defining challenge of applied AI right now. Context engineering isn't just a neat prompt trick anymore. It has become the literal infrastructure of digital memory.
It really is the ultimate cure for the amnesiac employee. But, hearing how structured and statistical this dreaming process is, it leaves me with one final thought to mull over.
Oh, what's that?
If this orchestrator agent, this head teacher, is explicitly designed to only update long-term memory based on prevalent patterns and fleet-wide trends, what happens to the weird, beautiful, anomalous edge cases?
That's a good question.
If an AI system only learned from the statistical majority of its failures, are we accidentally building architectures that are structurally forced to forget the unique outliers in favor of the average? Do we lose the creative anomalies just to ensure the standard tasks run perfectly?
Something to ponder.
Definitely something to think about the next time you catch your AI repeating a mistake. Thanks for joining us on this deep dive.